But here we go. Oops. Let's try this. Okay. So most importantly in this talk, I want to congratulate Mary. Mary has contributed so strongly to the area of separation science that this is spectacular that she's receiving that award and she's just so incredibly deserving. She has contributed very strongly in both our understanding of fundamental science and chromatography, and is also driving the field in terms of applied biochemical sciences. So I'm very happy to be able to congratulate her on that. What I'd like to do, though, Mary and I have some similarities in what we're up to, but from different vantage points. We're both working with significantly sub-micron type materials and doing separation science on them. And so what I'd like to do is show you a little bit of the work that my group is doing with nanoscale type materials and their nanofibers. And I'll also show you some very unique mass spectrometry, which is also separation science, and the nanomaterials has really had a huge impact in that. So what we're doing is ultra-thin layer chromatography. Our films are typically no more than about 10 micron to 15 micron in thickness. We're using non-traditional stationary phase structures in that they're nanoscopic. Other people have used TLC for a long time, but it has low efficiency and is typically very bulk scale type of technology. What we're doing is electrospinning. Electrospinning is a lot like electrospray, but you have a thick polymer solution that you're spinning now. And basically, you apply a high field to a solution of a polymer and then move that high field to a conducting receiving plate. This is a diagram that shows that. In electrospinning, you get a Taylor cone just like you get in electrospraying, which is basically where the solution suddenly splays into a million little fibrous networks if you have a polymer solution, and you see that on the far right. I'm going to show you just a summary of some of the things that we've done recently. Some of the first work we did was with polyacrylonitrile, UTLC, and we also made carbon UTLC plates. I'll show you that. You can make particles, you can make fibers. There's a lot of control that you need, just like in Dr. Worth's area, that you can make this, but to make it well is still a bit of an art. This shows you that as we electrospray, you get this fibrous network that looks like this. Oops. And we have two things here. This is a commercial UTLC separation where we've looked at some steroidal type compounds, and this is retention indices, and you see that the commercial, you get as a function of composition, you get variations that look like this, and on our nanoscale materials you get variations that are similar in structure but even with the same composition, and both of these have nitrile phases. You don't get the same exact variation as a function of composition of the mobile phase, because there is differences in the density of the nitrile group between the commercial phase and the UTLC phase. What has been most spectacular about this, and continues to be so, is that these UTLC plates have just incredibly high efficiencies. So this is the best commercial UTLC plate in terms of efficiency. This was the nano silica cyano, and we had efficiencies that could get up to 1,000, but for these nanoplates, nanofibrous plates, this was our first foray, our first attempt at this. We're getting significant number of theoretical plates, and all of what you're going to see today is separated in less than 2 centimeters. So it's very high efficiency and short amount of distance and also time. A lot of the reason for this is the spot sizes stay very, very sharp, as opposed to what you see on the far left is what you get with the best UTLC plate that we could get. And as Mary pointed out, with nanomaterials, you also see that here we have the nanosilica, the commercial phase. This is a commercial silica plate, and you see that distance traveled as a function of square root of time. Our pan plate, the analytes are moving at a much higher clip at the same distance. And so it's an issue. What gives you that high efficiency is both speed of the separation and also the tight band dispersion that you get. This is history now, and this is too, but this so far is our absolute most efficient phase, and it's carbon. We made a carbon TLC plate by pyrolyzing a photoresist and decided to do a separation of essential amino acids that you see here. These are the retention factors that we got. If you change the processing condition to make the carbon, you get different retention order, and our group has specialized in carbon for a long time, and so that's simply because the carbon microcrystallite changes as a function of the size changes as a function of distance, or as a function of processing temperature. But this is the most important thing, and this is a separation that we got of the essential amino acids, and this is a separation, as I said, in 2 centimeters. And this is the quality of this separation is something that you would expect to get in CZE. Here's the plates, the plate numbers that corresponded to that. So hundreds of thousands of theoretical plates that were corresponding to that chromatogram, and just incredibly reproducible. So when you get that kind of efficiency and you also have carbon, you also get resolution that is also off-scale high compared to anything you'd expect on a TLC plate. And so this is the resolution comparison between a commercial phase and our phases that you see here, carbon. The other unique thing about these nanofibrous material type UTLC is that they're not behaving, as Mary has pointed out, like you would expect to see with the micron scale type technology. With capillary flow-based TLC, which is the only thing we've done so far, you expect the band dispersion to increase as a function of distance traveled. This line is our work. We actually see that it either stays flat or it goes down as the band dispersion as a function of distance traveled. So we can make really large devices, likely because of this behavior. Okay, so to summarize what we have so far on that, we have made an incredible number of UTLC plates over a large number of different types of polymers, carbons. The carbon can get 2 million theoretical plates per meter. All of these devices are incredibly both chemically and mechanically robust. Well, all right, I guess it didn't save, but I was going to show you some work that is under review right now. We have silica-based UTLC plates these days. The silica nanofibers are about 300 nanometers in diameter typically, and we're getting high performance out of those too, but not as high as the carbon. So I apologize. I thought I had saved that back in the room when I was making this quick talk, but obviously it didn't save. So the other thing I wanted to show you, which is really quite remarkable, is I want to show you a little bit of our mass spectrometry. Mass spectrometry, after all, is nothing more than separation science. And we decided to simply, somewhat on a lark, but also knowing that these carbon materials were very interesting, we wanted to see what many of these nanofibers would do as a MALDI substrate. And if you recall, MALDI functions in that you have your analyte and it's co-crystallized with a matrix, and that matrix, we now know which matrix we want to use for MALDI, and it's a matrix typically that is typically a matrix that's an organic acid, and it absorbs UV light, the laser beam, from the laser beam that's being placed on the surface. Well, there's also another type of substrate too, but before I get to that, typically MALDI is done on inert substrates, either gold or stainless steel. This technology does have some limitations in that you have to, this is a bit of an art. You have to learn how to co-crystallize analytes reproducibly into these small crystals. When you do this, you also get basically an inhomogeneity in the surface, and you have to look around for, quote, the hot spot, where you get the most signal. There's also a problem with MALDI because you have this material that you're co-crystallizing your analyte with, and so you've got interference at the low mass range because of matrix. Others have done what's called SALDI, surface-assisted laser desorption technology, and there they take nanoscale inorganic materials that do absorb UV light. They get minimal low-mass interference, they have a homogeneous solid surface, and so they get decent mass spectra. And there's also matrix-enhanced SALDI, and that's where you take that UV-absorbing surface and you apply your standard matrix to it. Again, the surface allows the suppression of that matrix mass spec signal at the low mass range. SALDI, there's metals, precious metals that have been used, a whole carbon's been used, a whole array of very small structured materials. Porous silicon is very common when used. It works reasonably well. The problem is with SALDI you get low ionization efficiency of large molecules. Oh, well, there it is. there's the silica. I didn't get it moved right. There's the silica fibers that we've made and the efficiency that we're getting to date. So sorry about that. But as you see, the efficiency of this technology is truly increasing as a function of distance traveled, and that's very, very different than what you see on standard TLC plates. But there's chromatography. So back to mass spectrometry. All right, so SALDI has issues. As I said, it's got low ionization efficiency. To date, the highest molecular weight that you can see with SALDI is about 150,000. MALDI, the highest, has been 1.5 million. People who are facility operators don't like to see SALDI used or nanoscale materials because they say the nanoscale materials are damaging their mass spectrometer. And also, as I mentioned, only UV-absorbing materials have been used to date as SALDI devices. Okay, so we took some of our nanofibrous materials, and the fibers that we actually used are 195 nanometer or 150 nanometer, depending on the processing conditions, and you can see the MALDI plate and also the SEM image of these fibers. And this is the beautiful mass spectra that we get out of this. So we have polyethylene glycol, average molecular weight of about 3,400, and we get nice, very reproducible, high-resolution signal-to-noise mass spectra, better than what you would get on the far left with simply stainless steel with a matrix. And here, this is work that was done using another type of graphite surface, but with other graphite materials, they've been adding glycerol to dissipate heat. We don't have to do that. This shows you that the processing conditions that we have for our carbon does impact what we see, and the 800 is actually better than the 600. We get fragmentation of the analytes at the lower mass. Other things with the carbon, we have no interference on the low mass range. We can get low molecular weight analytes with very high resolution and high signal to noise with this carbon material. And this has been published. I just didn't update that. But we get very clean spectra. As I mentioned, ionization efficiency of SALDI is poor, and so let's look at ours and see what happens there. Well, here's another thing that's just out of control, incredible. This is polyethylene glycol samples. This has a molecular weight of approximately 900,000 molecular weight. These is the mass spectra, and it's doubly charged ions of this. And basically, we've run off the far end of what the mass spectrometer can see in terms of the large molecular weight. And so we see multiply charged ions, and we've got significant signal from this carbon nanofibrous substrate. Okay, so we tried some of our polymers too. We didn't think this was going to work, but why not? We have our TLC plates, and so we tried polyacrylonitrile and also SU8, which is an epoxide polymer, and tried to see what those things would function as far as a solid support for MALDI. Believe it or not, you place polymer on top of polymer fibers, you get incredible signal. This is polystyrene, 4,000 molecular weight. We have very clean mass spectra there. Using our pan substrate, SU8 is not as good, but high signal to noise. And the other interesting, very interesting attribute about this is these two particular polymers do not absorb UV light at 337 nanometers. And the whole concept of how ions are formed by MALDI or SALDI seems to be a bit flawed because we're getting incredible signal here. Okay, so shot-to-shot reproducibility for MALDI and SALDI is horrible. We're getting very reproducible signal with our technology compared to those which typically is as much as 400% change with shot-to-shot. Okay, other things you see. If we use polyvinyl alcohol now, substrates that have, these are nanofibers that are around 250 nanometers in diameter, and this is matrix-assisted SALDI now, with proteins. This is angiotensin 1. We get molecular ion of angiotensin 1, very strong signal of that with the matrix. And incredible detection limits too. The detection limit with angiotensin 1 with the matrix assisted is now 400 attomolar, and that too is a new record. The limit of detection with mere MALDI was 1 femtomolar, and the SALDI technology is always worse. And so we have beat MALDI, we have also beat SALDI by a long shot. So we also have basically minimal interference, as one might think. And so these nanofibers are actually quite good for separations in general. They are good for chromatographic separations. They are good for mass spectrometric separations. And so we are incredibly pleased to see the breadth of the applications that we're seeing here. And in many previous Pittcons, we've also shown that these nanomaterials are just spectacular for solid phase microextraction too. And so what I'd like to do is, and most importantly, thank again Mary, and thank you for listening to this talk that was impromptu. The cost of these phases are dirt cheap, markedly cheaper than your average TLC plate. If we can make these plates, I would hate to tell you how cheap these things can be made. Each plate is definitely less than $1 to make, probably less than 15 cents to make, honestly. They are just phenomenally cheap to make, and the amount of material we use and the support, very inexpensive. Yeah. So the time at labor is not high either. The only issue right now is that, like I said, there's some art to this. You can't just go electrospin and expect it to work. The art has been generated in my group, but we can reproducibly make these things just until we're blue in the face, and then some. So, yeah. Yeah. Chuck? Multi-electroweigh MALDI is difficult, but your spectra look very clean in the low. Yes, we get very high signal to noise. We have no interferences at low molecular weight. The fibers are macroscopically long. The other interesting thing is if you look at the damage that you get from the laser when you ablate the surface, you're getting minimal ablation too, and very minimal, which is also shocking. Yeah. So yes. We have indeed. We've published on that. You can make pattern devices that without any trouble. We've done a little bit of microfab, and it works very well for that. We even have molecularly imprinted nanofibrous materials. Yeah. Patterning, you can pattern down to the size of the nanofiber. It's easy. Yeah. Yeah. Thank you.